Here we're going to find the value of an infinite sum using a couple of really nice strategies. So in particular, we're going to be looking at the sum as n goes from 2 to infinity of n to the fourth plus n to the cubed plus n squared minus n plus 1 over n to the sixth minus 1. And before we get started, I want to notice that this converges by the limit comparison test. So it's kind of obvious to compare this to the series 1 over n squared. And that's because the dominant term in the numerator is n to the fourth. The dominant term in the denominator is n to the sixth. That reduces to 1 over n squared. And if you perform the limit comparison test, you'll get a limit of 1. But a limit of 1 will say that this series does the same thing as the series 1 over n squared. We know that to converge, so that means this thing converges. Okay, so armed with that, we can start thinking about how to find the value of this series. And what we should maybe think about is how to arrange the numerator and the denominator in a way so that some stuff cancels and we get simplification. So maybe let's look at the denominator, for instance, and all of the different factorizations that we could have of the denominator. So maybe the first one we could see is n minus 1 times n to the fifth plus n to the fourth plus n cubed plus n squared plus n plus 1. Well, to decide if that's going to be a factorization that's helpful, we'd like to see if any of these two terms will cancel with something in the numerator just immediately without rewriting anything. And I don't think they will. Notice if we plug n equals 1 into the numerator, that does not zero out. That means n minus 1 doesn't factor out of this. Furthermore, this sum n to the fifth down to 1 is probably a little bit too hard to work with on its own. Okay, the next thing that we'll do is notice that 6 is equal to 2 times 3. So we can think about this as n squared cubed minus 1. And then use the difference of cubes formula. So that's going to tell us that this thing factors like n squared minus 1 times n to the fourth plus n squared plus 1. Now, this is maybe a little bit more helpful because this n squared minus 1 in turn factors into n minus 1 times n plus 1. And maybe we can get some simplification out of that. And also, this n to the fourth has the same degree as this numerator. So maybe we could rewrite the numerator in a way that some of this stuff cancels. So let's maybe hold on to this factorization and see if it's helpful a bit later after we explore maybe the other obvious factorization that we have here, which is viewing n to the sixth as n cubed squared minus 1. So that inspires a difference of squares factorization. So we could factor this as n cubed minus 1 times n cubed plus 1. But I don't think this is super helpful because none of these really look like they can simplify with this numerator very well. So let's see. This is probably not the way to factor the denominator in order to make a nice simplification occur. This also is probably not the way to factor the denominator. So this is our best guess at the moment to factor the denominator using this and hopefully rewrite the numerator in a way that will create some sort of nice simplification. Okay, so now that we've made that decision, let's jump into the solution. On the last board, we motivated how we will factor the denominator in a way that will simplify the numerator a bit, or at least we came up with a good guess of what is the correct factorization in this case. So let's just write that down. And while we're writing it down, I'm going to write this infinite sum as the limit of the partial sums. So in particular, I'll write this as the limit as capital N goes to infinity of the sum as n goes from 2 to capital N of, I'm going to leave my numerator as is for now. So n to the fourth plus n cubed plus n squared minus n plus 1. and then I'll go ahead and factor that numerator out. Let's recall I was using n squared minus 1 and then n to the 4th plus n squared plus 1. That was visualizing this n to the 6 minus 1 as a difference of cubes. And then before we get too deep into the solution, I'd like to point out that we're starting the sum at n equals 2 instead of n equals 1, because n equals 1 would give us a 0 in the denominator. So maybe that goes without saying, but I'll go ahead and say it. Okay, next up, I'll take this guy right here and notice that it includes an n to the 4th n squared plus 1. So that motivates us to split what I have underlined in green and what I have underlined in purple into two parts. So let's go ahead and do that. So here we'll have the limit as capital N goes to infinity, and then we'll have the sum as n goes from 2 up to infinity of n to the 4th plus n squared plus 1 over n squared minus 1 times n to the 4th plus n squared plus 1, and then plus another sum as n goes from 2 up to capital N. Sorry, that should have ended at capital N. And now we'll have this purple bit. So let's see, that's n cubed minus n over n squared minus 1 times n to the 4th plus n squared plus 1. So we can end these parentheses here, and then also notice that we can freely pull that apart into two sums, because at this stage it's just a finite sum within a limit. Okay, so just to reiterate where these came from, this one that I've overlined in green comes from these terms up here that I underlined in green. And then this sum that I've overlined in purple comes from the terms up here that I've underlined in purple. Okay, so now let's notice I've got some obvious simplification. This entire numerator cancels with this denominator, or this portion of the denominator, and leaves us with a 1. Furthermore, we see that this n cubed minus n has a pretty obvious factorization, which will help us out with this denominator here. In particular, we can write this as n times n squared minus 1, and then cancel this n squared minus 1 with this n squared minus 1. Okay, so we've done quite a bit of simplification. Now let's rewrite this thing so we can get a handle on what's going on. So we've got the limit as n goes to infinity of our sum as little n goes from 2 up to capital N. Now we're left with 1 over n squared minus 1, and then plus we've got our sum as n goes from 2 up to capital N, and we're left with n over n to the 4th plus n squared plus 1, like this. Now, you've probably seen this first sum before. It's pretty classic kind of first example of a telescoping series that you might see in a Calculus 2 class. So we're probably going to want to use the fact that this n squared minus 1 factors as n minus 1 times n plus 1 in order to form some simplification. And that's what we'll do on the next board. And being motivated by that, we probably want to think about how this guy factors as well. So generally, when building these problems, there's some sort of symmetry in the solution methods that are used in the parts. So since this will factor out and then be solved using a telescoping series, perhaps this is also a good strategy for the second sum. And if you play around with it a little bit, this denominator over here also factors. It's not quite as simple as what we've got in this left-hand term, but it's not that bad. So we get n squared minus n plus 1 times n squared plus n plus 1. So I'll just let you guys check that if you multiply these two terms together, you get n to the 4th plus n squared plus 1. So let's bring this up with the factored form, and then we'll talk about how to split these apart. On the last board, we got our goal sum down to the following two sums that are inside of this limit. Furthermore, we talked about the probable need to factor these denominators and then split them apart. And the method that we use to split them apart is partial fraction decomposition. So let's do that in these side calculations. So I've set them up here. We'll take this 1 over n minus 1 times n plus 1, and write it as a over n minus 1 plus b over n plus 1. So now we can clear the denominator here by multiplying this whole thing by n minus 1 times n plus 1, and that will change our rational function equation to a polynomial equation. So let's see what it leaves us with. On the left-hand side, we'll be left with just the number 1 because that totally cancels this denominator. And on the right-hand side, we'll have a times n plus 1 plus b times n minus 1 after canceling the appropriate denominator. Now we've got a couple of choices in order to finish this off. Maybe we could compare coefficients on each side of the equation, but that's what we're going to do for the second decomposition. So instead, I'll use another algebraic approach where we set n equal to values in order to simplify this right-hand side. So notice if we set n equal to -1, that immediately gives us the equation 1 equals -2 times b. So in other words, we have b equals -1/2. So let's talk our way through that real quick. If n is equal to -1, that makes this term go to 0. Now let's in parallel set n equal to 1 and see what happens. So that's going to send this term to 0 because we'll have 1 minus 1. And then we'll be left with 1 is equal to a times 2. In other words, a will be equal to half. So all in all, we found our values for a and b. A is a half and b is -1/2. So now let's look at this second one. There's a little bit more going on here, but we're going to start off with the same strategy. So I'll multiply both sides by the denominator in order to clear all of the denominators. I won't write that out, but we're just multiplying by this term right here. And that's going to leave us with n on the left-hand side of the equation. And on the right-hand side of the equation, we'll have c times n squared plus n plus 1 plus d times n squared minus n plus 1 after canceling out the appropriate denominators. Okay, now we'll compare coefficients of each power of n on both sides of the equation. So let's see, we need to compare the constant terms on both sides of the equation and the coefficients of n on both sides of the equation. You might say we also need to compare the coefficients of n squared, but let's notice that the coefficients of n squared on the right-hand side is c plus d, on the left-hand side is 0, and that's the same thing as the coefficients of the constant term on the left and right-hand side. So we don't actually get any new information in this case looking at the coefficients of n squared, though in general you would need to do that. Okay, so the coefficients of the constant terms on the left-hand side and the right-hand side. So on the right-hand side, we have c times 1 plus d times 1. In other words, we have c plus d. Then on the left-hand side, we have 0. There's no constant on the left-hand side. And then the linear terms, so the n to the first power terms. So over here, we have c minus d. And then over here, we have 1. So we've got this nice system of equations here. C plus d equals 0, and c minus d equals 1. So putting this together, you'll see that c is equal to half, and d is equal to -1/2. You can find that a number of different ways. Maybe add these two equations and see you get 2c equals 1. Divide by 2, you get c equals 1/2. Okay. So all in all, we're able to split this term into 2 and this term into 2. So let's jump to that being written at the top of the board. So in the last board, we got down to the following step, which I've separated out a little bit. So we have this thing with two sums that were both rational functions, used partial fractions to split those apart, and that's what we've ended up with here. But now let's look at this sum versus this sum, the first versus the second. Notice they're offset a little bit. Here we have 1 over n minus 1, and here we have n plus 1. So with some re-indexing, we can turn one of those into the other. And so that's exactly what we'll do here. So what re-indexing should we do? Let's see. Maybe I'd like to take every value of n here and replace it with n plus 2. So notice that's going to change n minus 1 into n plus 1. And while it changes n minus 1 into n plus 1, it's going to change this lower starting point and this upper ending point as well. So let's notice if n plus 2 is equal to 2, then that means n is equal to 0. So that means our new starting point is n equals 0. And then our ending point, well, if n plus 2 is equal to capital N, then n is equal to capital N minus 2. Oh, and then I almost forgot, we're changing this n minus 1 to an n plus 1. So that means we can get rid of this old starting point. And then we have now the sum as n goes from 0 to n minus 2 of 1 over 2n plus 1. I guess I should say 2 times n plus 1. So now these two guys almost look exactly the same, except for the starting and the ending points, which we'll take care of in just a bit. But now we want to perform a change of variables on this sum. So instead of sending n to n plus 2 here, we want to send n to n plus 1. So let's see, if n is sent to n plus 1, then that means n squared becomes n plus 1 squared. And then we have minus n plus 1 plus 1. Multiplying this out, you see that we have n squared plus 2n plus 1 minus n minus 1 plus 1 after distributing everything. But notice that everything cancels as it should. So this plus 1 and minus 1 cancels, and this minus n cancels this down to just a n with a coefficient of 1. So that changes this denominator into that denominator over there. So that's good. So I can change this to a plus. But I have to re-index the starting point and the ending point while I'm at it. So if n plus 1 equals 2, that means n is equal to 1. So my new starting point is 1. Then furthermore, if n plus 1 is equal to capital N, then n is equal to n minus 1. So my new ending point is n minus 1. Now that we've gotten all that taken care of, let's start some simplification. So we've got this limit as n approaches infinity of, I'll take out the first two terms here, so that'll be the 0th term and the first term. Let's notice the 0th term is a half. The first term is 1 over 2 times 2, so that's going to be a quarter. And then we'll have left over the sum as n goes from 2 up to capital N minus 2 of 1 over 2 times n plus 1. So that's all from this first bit. Okay, nice. Now let's see what we have here. So we're going to have minus the sum as n goes from 2 up to, I'll stop at n minus 2 again. That means I need to include a couple of extra terms of 1 over 2 times n plus 1. And then as promised, I have to include the n minus first term and the nth term. So the n minus first term will be 1 over 2 to the capital N, 2 times capital N, because capital N minus 1 plus 1 is capital N. And then also we'll have minus 1 over 2 times capital N plus 1. Okay, so this entire line is just coming from these two sums. Now we'll do something similar for these two sums. This one, we'll want to take out the first term because this sum starts at 1, whereas this one starts at 2. So the first term here is 1 over 2 times 1 plus 1 plus 1. So that's 1 over 2 times 3. That's 1 over 6. So we have 1 over 6 plus, now I've got the sum as little n goes from 2 up to capital N minus 1 of 1 over 2 times n squared plus n plus 1. Okay, so we've sorted out this. Now let's sort out that next one. So that'll be minus the sum as n goes from 2 up to capital N minus 1, keeping in mind that we need to add the capital nth term on at the end, or subtract it in this case. We have 1 over 2 times n squared plus n plus 1, and then minus 1 over 2 times capital N squared plus capital N plus 1. So that's everything sorted out where we've re-indexed all the sums for easy combination. Now we've got some really nice simplification. Notice this sum is exactly the same as this sum now. So we can just cancel these things out. That cancels with that. Furthermore, this sum is exactly the same as this sum, but they have opposite signs. So we can just cancel these two out as well. So we're left with a half plus a quarter plus a sixth, and then all of the rest of this stuff that has a capital N in the denominator. Well, let's write that out. So we've got the limit as capital N goes to infinity. And then maybe let's combine these while we're at it. So a half is the same thing as 6 over 12. Notice the common denominator will be 12. A quarter is the same thing as 3 over 12. And then a sixth is the same thing as 2 over 12. So in the end, that is going to add up to 11 over 12. And then we'll have minus 1 over 2 times capital N, minus 1 over 2 times capital N plus 1, minus 1 over 2 times capital N squared plus N plus 1. But check it out, as capital N goes to infinity, those things zoom off towards 0. So that's pretty obvious because we've got things growing larger and larger and larger in the denominator while the numerator is just a constant. So in the end, we're only left with this term, 11 over 12. So that means the final value of our goal sum is 11 over 12. And that's a good place to stop.